All right, so on this first part, we were just practicing our first rule is if I have the value from this interval to this interval, and then do you see how here it's seamless? I know from -4 to 6, and then from 6 to 8. What I can do is I can go ahead and I can take that coefficient out, and I can just find the integral of those two. F of x dx is equal to this 2 plus this -5. Notice here, my numbers are opposite. So this is when we're going with the inverse. This is when we're going backwards. So that's why that negative is out there. So that becomes the opposite of -5. Here again, I have -3 to 2. And then I have 2 to 7. Here I have -3 to 2 of a different function. So this was just like our notes. If there's no interval, one of our properties said that therefore the accumulation is 0. If I'm talking about along the same interval of these two different functions, g minus f, I can take this output minus that one. And then, of course, here's where I'm going backwards. So again, I have a negative. In number 7, this 2 is a coefficient. When I integrate, just comes out to be a factor and multiply. That's the same thing that this 4, whether that coefficient's inside or outside the integral sign, it doesn't matter. How come this one cannot be determined? Because I know it from -3 to 2, I don't know anything about 1. So that cannot be determined, I don't have those values. And then here are these answers again. Anybody have any questions? They're called definite integrals because it's being calculated along a definite space. So step 1 is going to be to integrate following your rules from this a to this b. And then now that you have this function, this is your big function, f of x, because remember you started off with a rate. So this is your f of b minus f of a. So your f of b is going to be when you plug that b in to that original function, taking that output minus the a, and that difference is going to be the space in between on those intervals of that rate. So if you compare that to your trip project, if you were thinking about, okay, well, how many miles did I go in between this middle part of my journey, you would take the difference between those two times and you could figure that out. Anybody need the notes or the homework from this class? Sure. That's the pattern that we were looking for. Did anybody have a hard time with these? You want to talk about any of them? Oh boy. Sure. gonna need an extra piece of paper for these. So remember what we're doing here with finding integrals is we're going from rates back to my original function. So when we're talking about doing these integrals, sometimes it remembers it makes it easy, or it's important for us to remember the different kinds of derivative things that we did. Okay, so if we were given this as your original function and somebody asks you to find the derivative, so this here is your original function and somebody's asking you to find the derivative, which is the rate, how would you go about doing this, and what is unique about what you see here? Thank God. I was so afraid you would. Yeah, this is one of the ones where you need to use chain rule. How come? Yeah, because there's two ideas here. There's an inside and an outside function. So our outside conversation is going to be something to the 5th power. And our inside conversation is that 3x minus 4. So when we're talking about the chain rule, that's what we ended up using for some of these composite functions. So we're kind of peeling away layer and layer of what it is that we were doing. So if I'm finding my derivative, the first thing I'm going to do is find the derivative of that value, bring my exponent down as a factor, and then whatever's inside to the 1 less power. So that whatever's inside, that's a minus sign, whatever's inside, I need to also consider now this part here. And then when I take the derivative of that makes sure that I've considered everything. All right. So now what happens is we're just like we had to use that chain rule to account for the different layers of what was in our original function, we have to figure out how to do that backwards when we integrate. So far the things that we've been able to integrate have had to be kind of simple. And the only way that we could deal with the complex stuff is if we went ahead and either distributed. So we haven't had any product rules. We haven't had any quotient rules. We've had some shortcuts for things like trigs, for trig and logs, and exponents, but nobody's told us how to deal with products and quotients that we can't end up simplifying some other way. So our technique for doing that is going to be called U substitution. So just like we use the chain rule to find derivatives, we have a similar rule for taking the antiderivative of a composite function. So an antiderivative, remember, that's the same as our integral. And our composite function is when I have g embedded in an f of x function. It's called U substitution, which is how we do the chain rule in reverse. So if you look at what's going on here, we have this f of g of x times g prime of x. This should be similar to what we did that one lesson where we were doing inverses, where we had to take that chain rule. So what we're going to end up doing is for what we can't solve, we're going to go ahead and kind of bundle it up and put it aside for a minute, and we're going to give it another name and have that u be that inside of that function. So we say it's U substitution, and that's the common variable that mathematicians use. The same as we use M for slope, just because, and HK for the center of a circle, just because. U is what we're going to be using. Although you can use any variable that you prefer as long as you keep track of it. All right. So let's go ahead and think about what we have here as far as this rate of our function. And we don't know how to do this. And if somebody said, okay, well, why don't you simplify it first? remember the rule where I was like, look for ways that you can simplify it. So you're like, okay, because then this means that you need me to find the integral of 3x minus 4 times 3x minus 4 times 3x minus 4 times 3x minus 4 times 3x minus 4. And right now you're feeling a little lightheaded because you're like, oh snap, I can multiply this times this, and then this times this, and then that times that, and put it all together. And then I can get one long fifth power product that makes me want to cry. So there's got to be a better way. And here is the better way, because nobody wants to do that. Am I wrong? Would you rather do that? No. Okay. So what we're going to do instead is we're then going to integrate, and we're going to say, I am going to let u equal my inside. And over here on the side of my work, I'm going to go ahead and say that u is equal to 3x minus 4. So when I go to find and integrate, I have something that looks a lot simpler than I know how to do. We do have one problem. Anybody see the problem? Yeah. So this means that you're going to integrate in terms of x, which is not a problem because I have x's. This means I'm going to integrate my u in terms of x, but my variables don't match. So I cannot have this math problem happening in terms of x's when I don't have any x's when I replace the x's with a u. So I need to figure out a way to express my change in x's in terms of u. And this is why this is a little bit of the confusing part, because I'm going to go back over here and I'm going to say, oh, I know how to do that. And that's this part here. What are you doing there? What does this mean? You said it. Yeah, this is the derivative of this part here of what's inside. So the chain rule is a bizarre thing because it combines integrating and still taking the derivative. So I'm going to take the derivative du in terms of x. And when I take the derivative of this, I end up with 3. You okay with that? Awesome. Now I need to solve for dx. So it's like algebra 1 geometry proportions. Here we go. So depending on how you want to write this and how you think about it as a mathematical thinker, if you want to put 3 over 1, rock on. 3 times dx is equal to du. Dx is equal to du divided by 3. Your goal is to find another way of writing dx in terms of du. You find the derivative, du dx, the change in u compared to x, is equal to this derivative. That's this part you were talking about up here. And then all you got to do is solve for what you need. I really need this. Okay, so I'm going to do that magic that algebra is, where I manipulate it. And dx is equal to du divided by 3. Everybody okay up to this part? So now I want to integrate u to the 5th in terms of u. So what ends up happening is, instead of writing dx, I'm going to write what dx is equal to. So now, the cool part about that is I can do some more simplifying. I can say that this is the integral of 1/3 u to the 5th du. Now I'm in good shape. Now I can integrate because I am talking about it in terms of du. This 1/3 comes outside. It's the integral of u to the 5th du. So it's 1/3 of u to 1 higher power divided by my new power. Plus c. So now I have 1/18 u to the 6th plus c. That's a whole lot better, don't you think? So now what I'm going to do is I'm going to go back and get what I said u was equal to. And I'm going to say that 1/18 of 3x minus 4 to the 6th power plus c is my integral. And the pretty cool thing here is you can go ahead and find the derivative of that, and it'll take you back to 3x minus 4. Kind of cool, yes? All right, let's do another example. Here I have my 6x squared times this function raised to a power. So the interesting thing here is you have to figure out what it is that you're going to note as your inside-outside function. And this one's a little confusing because you have this product here times this exponent, but I want you to see this inside here. So I'm going to let u equal to x cubed plus 4. Now right now you might be a little stressed about what about this 6x squared, and what I'm going to assure you is the ones that we give you are fairly well designed that some pretty cool stuff happens and cancels out. And I remember saying that to my Algebra 1 students when I was teaching them polynomial division, and I remember saying that to my Algebra 2 students when I was teaching them operations with rational functions. The ones that we give you are designed to work out. So it's pretty cool when you can start see some things that'll start canceling out, and you can make some predictions about what's going to happen. So if I let u equal to this, I'm going to rewrite my integral as 6x squared times u, and I have dx. I can't have dx. Dx is not what I'm looking for. So I'm going to go ahead and take the derivative of u in terms of x, and I'm going to call this 3x squared. Yeah. Oh, u to the 5th. Nice catch, Adrian. You go put a smarty up. So this x is a problem. My dx is a problem. So what I'm going to do is I'm going to wind up figuring out a way to solve for dx. du is equal to dx times 3x squared. du divided by 3x squared is equal to dx. That's basic proportion math. And if you do enough of these, you'll wind up seeing the relationship between dx is going to equal to du times that. answer that was your derivative. See how that's happened twice so far? And pay attention to those values that end up in the denominator, because these values that end up in the denominator are what end up making this part of your equation simplify and cancel out. Because instead of writing dx, I'm going to write du over 3x squared. So if you were nervous about this x squared, are you nervous about it anymore? What do you think is going to happen to that x squared? Yeah, it's going to cancel out with this part of the denominator. The ones that we give you are designed to work out. So if you wind up with something in your integral that you're like, wait, I don't know how to do this, go back into your problem and look for something that winds up canceling out, because now I have, 6 divided by 3 is 2 times u to the 5th du. I can integrate that. My 2 comes out. My u goes to the 1 more power. I divide by my new exponent. Plus c. One third u to the 6 plus c, 1/3 times x to the 3rd plus 4 to the 6th plus c. So with u substitution, we end up pulling this part out. If you take a look at back here, if I'm trying to integrate a composite function, a function within a function, I end up multiplying by this derivative of this. And I could go ahead and do that through finding that derivative and expressing in terms of u, because u is what I replace that function with. All right, stay with me. Let's do example 3. So we have to figure out what our u is. Anybody have any ideas? Yeah, so if you're toying with, is it this one or this one, I can rewrite this as x to the negative 1/2 power. And then I can go ahead and let u equal square root of x minus 1 and have that times u squared dx. So let's go ahead and figure out how to replace that dx and make it in terms of u. So the derivative of this function in terms of x is going to be equal to, if I call this x to the 1/2 power, I get 1/2 times x to the 1 less power. So my du dx is equal to 1 over 2 times the square root of x. Taking that derivative, when I want to solve for dx, I'm going to do cross products. Dx times 1 and du times 2 times the square root of x. This is what I'm going to now put in for dx. And the interesting thing is now that I'm back here, I'm like, wait, I think I'm going to go back to having this be 1 over the square root of x. Now that I see, oops, why did I write a 3 in there? Nobody caught me on that? Because I'm looking ahead like, oh, cool, these are going to cancel out. So instead of dx, I'm going to say it's the integral of, and I can go ahead and put my u squared back over the square root of x. Pulling these out wasn't what was going to happen because now I see what is going to happen. And this is times du times 2 times the square root of x. So this here is what I'm putting in for dx, my du times 2 root x. Very cool. That ends up canceling out. So I'm finding the integral of 2u squared du. Not so bad. My 2 hangs out. My u goes to the 1 more power. Divide by my new exponent. Plus c. I can rewrite this as a fraction. My u is the square root of x minus 1 to the 3rd power plus c. That's my original function. This derivative was from this original function. It's cubed because I'm 1 more power. Divide by 3. Here's the 3. And again, it doesn't matter whether you write this as 2 times the square root of x minus 1 cubed all over 3 plus c. These two things are the same, depending on how you like to look at that coefficient fraction. All right, so when I want to integrate a tangent function, I look back at my chart in the back of the room. No derivative results in just a tangent. So the derivative of the tangent is secant squared. The derivative of secant squared is tangent. But look at that back of the chart. Nothing else comes clean. It don't end up with a tangent as the result of taking a derivative. So I don't have a way of doing that trig-wise. It doesn't work out for me. So what I have to do instead is find the integral of my sine of x compared to my cosine of x dx. So I have to rewrite that. Now, knowing that I need to plug something back in and do some more math and have some magic happen where it all works out, I have to make a decision about, am I going to have my u represent my sine or my cosine? So I'm going to think ahead about when I take that derivative. So if I have my u equal to, I have to think about, is it going to be my sine or my cosine of x, because I'm going to be finding my du dx, and I know that whatever I put in, I'm going to want to start making some stuff cancel out. So if I let u equal the sine of x, is that derivative going to work in my favor? If I let u equal the cosine of x, is that derivative going to work in my favor to cancel out what I need to. Any thoughts about what I should do? You like cosine? Let's try it. So when I take the derivative of the cosine, what do I get? I get the opposite of sine of x, right? Yeah? All right. So let's see what I'm substituting in. So dx times the opposite of the sine of x is equal to du. I just did cross products there. Are we okay on that? So now my dx is going to be equal to du over the opposite of the sine of x. Is that going to work out in my favor? Let's see. So I have the integral, I let u equal cosine, so I have the sine of x over u. And instead of writing dx, I'm going to write what dx is equal to. Du times the opposite of the sine of x. Am I able to cancel out what's in my way that I don't know what to do with? I don't know what to do with it. Watch. So I wind up with the integral of the opposite of 1 over u times du. This whole act of taking the derivative is just so I can make sure that I'm talking about the same variable. That's that taking that derivative of the inside of my function. This negative sign comes out as a -1. And now I have to go back and look for my rules about having 1 over u. If you look back at the derivative of the natural log of x, you end up with 1 over x. So now we have, anytime I have something to the negative first power or 1 over that, that derivative is the natural log. So the opposite of the natural log plus c. So then I can have the opposite of the natural log of the cosine of x plus c. All right, let's do this next one. I've got 5 times x times e to the 5x squared. What do you want u to be equal to? Let's go ahead and let u equal 5x squared. So I'm going to take the derivative, or take the integral of 5x times e to the u. And instead of writing dx, I'm going to figure out what dx is equal to in terms of u. So du dx is equal to, you okay with 10x? Dx times 10x is equal to du. Dx is equal to du divided by 10x. So this is what I'm going to write instead of that. The integral of 5x x times e to the u times du over 10x. What do you see that cancels out? My x's cancel out, and this 5 cancels out with that 10 leaving 2. So it's the integral of e to the u. Well, let's put my 1/2 in there. Let's bring that out. 1/2 e to the u du. What's the integral of e to the u? E to the u. One half e to the 5x squared plus c. All right, I want you to take a minute and process. I want you to write some notes to yourself, things you want to make sure that you remember for u substitution, things to keep in mind. Yeah. Say that again. Would it matter if what? So if you picked cosine and you put u in, it should work out, but you're not going to be able, the canceling out won't be as pretty. Because if you let u equal sine, when you, because you, that has cosine down here to the negative first power, so you end up getting tangled up in negatives. So if you want to try it and see if it works out, it's just not going to be as pretty. Yeah, I like those. Those are good. And I save them and use them just when they don't want. So when they're like the baddest at me, I'm like that back row. Go. I like my cartoon. Because like when you're writing a coupon book, you're like, oh, I'm gonna do the fish restaurant, oh, I'm gonna walk the dog. Or a rainy day like today. I thought the dog walk. All right, so this is so fun. We'll do the first one together. So I want to integrate this, x times cosine of 2x squared dx, and it says let u equal to that. So, okay, so that means that du in terms of x is going to equal to 4x, right? And then when I solve for dx, I end up with dx is going to be equal to du divided by 4x, right? So if I'm finding the integration of x times the cosine, and remember I let u equal 2x squared, so I'm going to the cosine of u, and that's going to be times du over 4x. So see how that x and this x cancel out? So now I'm finding the integral of 1/4 of the cosine of u du. So that's going to be, my 1/4 comes out, and cosine to sine of u plus c. So now I have to put my u back inside, right? So I have 1/4 times the sine of 2x squared plus c. So that looks like A to me, right? Everybody got that? So then what you're going to do is you're going to go to your potato head. And on your potato head, the answer to number 1 is A. So then you're going to go to your chart. And for number 1, if the answer is, here's A, B, C, or D. So for number 1, that means on your potato head, you're drawing these kind of eyes. So on your potato head, you're drawing these creepy big eyes. So you're good, right? And then, didn't I give you a hint already that 2 is D? Say yes. So now for 2D, oh, you get to draw this creepy toothy smile, right? I drew my top teeth way too small, so now my big teeth are huge. All right. You get it? Good. Have a good time. Go.